Okay, at the end of class we'd started talking about some of these limit properties, and I told you rather than continue talking about those in class that I would take some time and put a video together and discuss those. So here we go. We have our conditions here. B and C are real numbers, and is some positive integer that'll come up in a little bit. And F and G are functions who actually do have limits as x approaches C. Now, a couple of these we discussed last time, but they're also written down here. The first is that we're able to factor a constant out of a limit process, and then just take that constant b times the limit. And number two, if we have two functions that we can compute the limit of, and they're being added or subtracted, again, the limit essentially can distribute through the addition and subtraction. Number three says the same thing about limits as x approaches C of a product. Again, assuming the two limits exist, you can take the limit of each part. Now moving on, these are two that we didn't get to last time. You can also distribute a limit through a fraction, provided both limits exist, and also the limit as x approaches C of the denominator, in this case g of x, cannot be 0. Otherwise, this distributing limits through will not work. And finally, number 5, if you have a function being raised to a power, you know that the limit of the function exists, then you can evaluate that and raise that answer to the power. Now what I'm going to do here is, in a moment, is look at how we can prove a couple of these examples. Okay, so I want to take a moment now and prove number 1. I think I'll also go ahead and prove number 2. Proofs 3 and 4 are very similar to the proofs for number 2. So I want to prove number 1. So we begin by, well, let me just restate what number 1 says. And that is that the limit as x approaches C of some number b times f of x is in fact equal to the limit as x approaches C. Oops, I missed something. Hold on. B times the limit as x approaches C of f of x. Now, taking that one step further, we assumed originally that limit as x approaches C of f of x is equal to L. So this would be b times L. So to show this, we need to show that given some epsilon, so we need to show that given epsilon greater than 0, we can find a delta greater than 0, and then remember what that condition would have to say. So that if if 0 is less than x minus c, if that's less than delta, then absolute value of f of x, or in this case b f of x, minus the limit, which would be, we're saying it's b times L is less than epsilon. So here's how the proof works. We start, again, much like we did with the proofs for specific functions. Okay, back to the video, just a little interruption. A kid came to visit me. So we start with that condition again. We want to prove, we start with that and try to work our way backwards. So notice that we can factor a b out. Now technically b could be negative. B could be negative. So we're technically factoring out really an absolute value of b. So we have absolute value of b times the absolute value of f of x minus L is less than epsilon. And so then we can get absolute value of f of x minus L is going to be less than epsilon over the absolute value of b. Okay, now here's the key step. We know that f of x is in fact a continuous function. So moving off to the side here, we know I said continuous, please ignore what I just said. We know that the limit as x approaches c of f of x is actually equal to L. So what that means is for any value you pick, any value, I'm going to call it epsilon prime greater than 0, we can find delta such that if 0 greater than x minus c less than delta, then absolute value of f of x minus L will be less than epsilon prime. Now, how does that help us here? Well, we now have absolute value of f of x minus L being less than something. And so, by letting epsilon prime be equal to our epsilon over the absolute value of beta, for that size, we can find a delta. We can find a delta such that if the absolute value of x minus c is less than delta, then f of x minus L would be less than that epsilon prime. But if the absolute value of f of x minus L is less than epsilon prime, then it's also, of course, less than epsilon over beta. Right, the epsilon over beta there. And if that's true, then the absolute value of b times f of x minus L is less than epsilon. And so b f of x minus bl is less than epsilon. And we're done. But let me go ahead now and step through the process, though, so you can see how all the details now work. So once we've let epsilon prime be epsilon over beta, choose the delta that works for f. So we choose the delta that works for f. And now we can come out and say, okay, so since f is continuous, we know that if x minus c is less than delta, then we can say with full confidence that the absolute value of f of x minus L is less than epsilon prime. But that's the same as saying that f of x minus L is less than our original epsilon over the absolute value of beta b. And then that's the same as saying that absolute value of b times f of x minus L is less than epsilon. And then that is what we want it. B times f of x. Right, bringing that absolute value inside just like we took it out before. And b times L. Absolute value of that is less than the epsilon that we started with. Now there is one little minor detail with multiplying by b here that is an issue. I did divide by absolute value of b, so I was making an assumption that I never really stated, and that is that b is not 0. So this works for any b that's not 0. Well, what about if b is 0? Well, if you multiply a function by 0, then you're taking the limit of 0, and of course it would be 0. And so 0 also works out as well. Now you may need to go back and look over this a couple times, think about it yourself. Here in the next video I'll take a look at proving that a limit does in fact distribute over a sum and a difference. If you have questions, feel free to email me or ask me about it in class or after class. I'll be happy to try to go over it a little bit more. Thank you.